The purpose of this lab was to show an object consistent with Newton's second law. I then analyzed the object's motion using Tracker and recorded the initial conditions of the experiment. By inputting these initial conditions as well as other physics principles into the lab start code, I was able to create a computational model in VPython meant to predict the object's motion. I then compared the predictions of this model with the observational data collected from the experiment to see how closely they aligned. This comparison helps us to address the purpose of the lab, which is to show an object demonstrating Newton's second law of motion. Newton's second law states that the sum of all forces acting on an object are equal to its mass times its acceleration. The results of this lab demonstrate this principle, as gravity and drag force are acting on the falling object. This is the original video of me dropping the eraser from 1.7 meters at an initial velocity of 0. I then analyzed the object's motion by putting the video into Tracker. I placed the origin of the axes at the object's center of mass, and when dropped, the object moves in the negative y direction. I then set the calibration stick to my own height in order for Tracker to accurately analyze the object's motion. This movement is indicated by the red diamonds, which show the object's increased velocity as it moves closer to the ground. The inconsistent change in velocity indicates that the object has an acceleration, meaning that the net force acting on the object is not 0. The initial conditions of the experiment obtained from Tracker include the observed start time, the initial position, the initial velocity, the ending observation time, and the mass of the object, all shown here. These values were then used in VPython to create the computational models for the experiment. As input in the VPython script, the ball's mass is 0.02 kilograms, the ball's initial position starts with a slightly negative y, and the ball's initial velocity is 0, since it starts from rest. Because this first computational model does not account for drag force, the drag constant b is 0. The physics concepts used to create this code relate to Newton's second law. This law states that an object's final velocity is equal to its initial velocity, plus net force over mass, times the change in time. In this code, you will also see gravitational force as well as drag force incorporated. However, for this model, b is set to 0, so the drag force is non-existent. This means that when this code is run, the only force vector to be seen acting on the object is that of gravity, pointing down. Although this computational model does not account for drag force, the results are extremely close to our experimental data. As you can see, this code includes the gravitational force as well as the drag constant to account for the drag force. This drag constant was chosen because it came nearest to predicting the object's motion. As shown by the free body diagram, this model not only includes gravitational force acting on the object, but also drag force. When compared to the computational model that did not account for drag force, this model more accurately depicts the object's actual motion. This is because the model that did not account for drag, indicated by the green line, had no forces acting against gravity and instead overestimated the magnitude of the velocity. These findings concur with Newton's second law by showing that an object's acceleration is determined by the sum of all forces acting upon it. If an object were to be thrown downward, the object's terminal velocity would be the same as its terminal velocity when dropped from rest. However, it would reach this speed more quickly. Terminal velocity is not determined by initial velocity, but rather by an object's mass, density, and area, as well as the gravitational force and the drag coefficient. This means that a computational model that accounts for drag force could predict the terminal velocity of a falling object, because the terminal velocity is reached when the drag force equals the force of gravity.